briefly go over three topics that are kind of quasi-related to each other, and just use this in the last part of Class 5. I'm not going to go in depth or do any problems with them, but they're kind of interesting, and I figured to leave them out completely out of the course would leave a gap. So the first is section 315, talking about stresses in rotating rings. Those stresses really come from centrifugal force. So like if we take a look at the equations that these represent right here, we'll note that we have omega, which is the rotational speed in radians per second. That's squared, and we have mass, right? So these really represent, if you can recall, centrifugal acceleration from dynamics. These are causing this ring, because it's spinning so fast, wants to get larger, right? The mass wants to go outwards, but it's being held in by the material, and therefore there's going to be tangential hoop stress that's created by this thing spinning. There's also going to be some radial stress, and you'll notice that a lot of these parameters here. Well, notice that they have Poisson's ratio is in here in a couple of places, but no, you have the inside and outside radius. And note right here, this doesn't have a subscript, so this is a variable. This is a description of the distribution of these internal loads, which is what stress is, right? This also doesn't have a subscript right in there. Similarly, the radial, so that's the hoop stress right there, that tangential right there, and that's the stress that's coming outwards. If you have a stress element, that's the middle of this. We also have radial stress. Has a lot of the same traits that are in there. This is the only this parameter right there and that parameter both have no subscript. So these have like sort of a similar type of distribution. I've plotted them right, with some numbers, right? So anytime you see an equation that gives you that, it gives an opportunity to plot it and put it together, put some numbers against it and do it in Excel. Sometimes it's used Unity, but in this case, I chose a ring that had an inside radius of 2 and an outside radius of 5. I probably picked a Poisson's ratio of like 0.3, which is sort of typical. And probably just pick some large number for the angular velocity in radians per second, and is some density. But anyway, I monkeyed around with some numbers just to see what these distributions would look like. And it's interesting, you could see that the radial stress is 0 on the inside surface and 0 on the outside surface. It's also interesting to see that the tangential, the hoop stress, is larger on the inside, and it starts to diminish. It doesn't go to 0. There is a value here on the outside. And some application of this might be, I don't know, the rotating hub of some fan, or maybe even a turbine blade in the compressor or the turbine section of a gas turbine. Somewhat similar, but not quite. And the thing that maybe I should have said this out loud, but notice how similar this is to a pressure vessel, right? The idea of the tangential and the radial stresses being involved. Although the radial stresses are due to the thing wanting to get larger, and really the interrelationship of the directions, which is what Poisson's ratio is describing, is that something happens in one direction, it affects what's happening in the direction perpendicular to it. Now, a similar, somewhat related is section 316, where we have press fits and shrink fits. A number of equations. I'm just giving you a guided tour. If you look a little more closely at it, you can see that equation 356 has 2 different materials in it. Well, first let me take a step back. The idea for some pieces of equipment, you want to join them together, and one way of doing that is to first have an outer piece that has a hole in it that's smaller than the inner piece's diameter, right? So if you tried to put these together, they wouldn't fit. But if you heat up the outer one, Or if you cool down the inner one enough, there can be enough expansion of the outside one or contraction of the inner one, and you can get them to fit together. And then when they come back up to room temperature, they will now be fit together. And there's going to be some residual stress. There's going to be some stress in between the two parts because they're trying to go back to their original size, but they can't quite. They either the outside's going to be stretched or the inside's going to be compressed, or a little bit of both. So the pressure in between these two surfaces is what's being described here in equation 356. When you have two different materials. And you can see that this del right here, that's the amount of interference. That would be the difference between, I guess, the radius of the outer one and the radius of the inner one. This next equation, this is if they both have the same material, right? A lot of things cancel down. And if you wanted to figure out what the tangential stress is going to be for this piece, on the inner and the outer, you can see here are what the two pieces is going to be. So the inner piece, okay, so this is when this is at a location where little r equals big R, right? So that's going to be like right there at the interface. You're going to see what the stresses are. The hoop stress on the inner part are going to be this. It's going to be compression. And on the outer part is going to be this. They're very similar to each other. So anyway, this would be an interesting thing to do because, or a thing to find out. One reason you might want to know this is because these parts might also be in operation. Heck, they could be spinning because now some of the other stresses that they might experience might be because of rotation, right? You need to combine stresses, and you need to combine stresses intelligently in order to calculate what the actual operating stress is going to be, or to go backwards and design it so that it doesn't fail. And so the last topic I will do an example on, and it's quasi-related because I talked about having to heat the thing up in order for it to expand, to be able to put this interference fit together. Well, I think that kind of like implies that things expand when they get hot and they contract when they get cold. You already know this. Well, we can use the coefficient of thermal expansion to try to predict or to predict, I guess, how much that's going to happen. So it's a material trait, this coefficient of thermal expansion, and you can see that it had the units of 1 over degrees, either Celsius or Fahrenheit. Something that I think is kind of interesting is to see aluminum compared to steel. Aluminum has a lot more coefficient of thermal expansion than steel does, almost 2.5 times. That's kind of an interesting relationship or thing to keep in mind. I'll even bring it up when we talk about welding in ME370 because it's one of the big difficulties of welding aluminum is that it will distort a lot when it gets heated up. But the equations that they present here is that the strain, simple strain, is going to be equal to, and it's going to strain in all three directions, right? It's going to be equal to the coefficient of thermal expansion, alpha times the delta T. And in the special case where maybe you have a bar that's constrained between two very rigid locations, and you have a bar in between here, here's my pencil right there, and you heat it up, but it can't get beyond these much more rigid surfaces right here. It wants to have strain and elongation, but it can't have the elongation, so it simply has the strain, and that you could find the stress from by just the simple Hooke's law, where stress is equal to strain times Young's modulus. So that's that's the reason why there's a negative there. In that scenario, it would be under compression. So I have an example right here that I want to put through. One thing that I tried in several years ago, I created a homework problem where I tried to have all kinds of things happening at the same time. I thought it was kind of neat, but it was pretty ambitious. Let me describe it real quick. I had a heat exchanger, right? So we had this heat exchanger. Looks something like this right here. And it was really heavy. right? So it was so heavy that it was like a distributed load, almost a distributed load. You had to worry about it, right? So it had this distributed load type of property to it. So it had some bending, right? That was going to be there, but it was also a heat exchanger. So it was a pressure vessel. It also had some mounts. And I made the mounts look like kind of like this right here, so you could see that it was like mounted on these spots. And somebody had fabricated it poorly. So on one end it was like this right here, but on the other end, for some reason, somebody had misaligned the other end, right? And then they clamped it down really tight. And not only that, did they clamp the thing down tight. When they clamped it down tight, it wasn't allowed to expand. So it had all these possibilities of stresses. It had stresses because it was very heavy and it was trying to sag, right? So it had the bending moments that are going to be caused, like a kind of like a simply supported beam. But I guess we could say that it could kind of pivot about these points. This is really far-fetched. I was trying to make something very complicated. And it had some torsion on it, right? So we were saying somebody just cranked this thing down, cranked down the bolts, even though it didn't want to be twisted like that. They forced it to twist at a certain angle right there. And that too is going to cause the thing to be strained, right? In that twist. And, by this right here, right? I think it's TL/JG, right? So if we had that angle right there and we knew the length and the cross-sectional property and this modular elasticity, we could find that's the torque that's being placed on the thing. Let's see, what else? And then also the coefficient of thermal expansion was causing actually compression onto the thing, I should say. But it also had longitudinal stress and it also had tangential stress. It's a very complicated problem. Maybe it was overly complicated problem. But here's a more simple problem, and this is out of Philpott. And we have this bar right here. So we have this 25 millimeter diameter bar that's 3.5 meters long. So it's a fairly long thing going on here, 3.5 meters. And it's 25 millimeters in diameter, so that's 1 inch, right? And it's stress-free when it's attached right here. And then here at the end, it has got a 16 millimeter bolt right here. So this one is 16 millimeters. And determine the normal stress in the rod, in this rod, and the shear stress in the bolt after the temperature drops 60 degrees Celsius. So we want to use, and I think are both of them made out of steel? To determine the steel rod and the stress in the bolt. They must be both steel. Well, this one is steel, right? What about the bolt? Do they tell us anything about that? Well, I guess we don't need to know that. All right, cool. So basically, it is a simple thing. We could find the area of the rod is going to be pi over 4, 0.025 squared, and we get 4.909 E minus 4 meters squared, right? So that's the cross section of the thing. The delta T is going to be a negative 60 degrees Celsius, so it contracts. So the deformation that it would have if it could, right? The del that it would have would be FL over AE. Right, that's what it. If you had an equation for if you apply a force to something, this is the amount of deflection that you get. But it's got to be 0. So if you add in the the alpha delta t and times length, that right there has to equal 0 because it can't deflect. It wants to deflect, so it can't deflect. So we stick the force in there. At the force, the length is 3.5. The area, 4.909 E minus 4. The elastic modulus was, they said it was 200 gigapascals, right? That's E9 for newtons per meter squared, right? Giga is the 9. And then this is really, well, I guess we'll say plus here. And the alpha, they told us that was going to be 11.9 e to the minus 6. 11.9 e minus 6. And the delta t was negative 60. There's where the negative is going to come in. And the length of the thing is 3.5, and that equals 0, right? So you can see that's going to tell us what this force is going to be, and that's going to be 70.10 kilonewtons. So that's the force that's going to be in compression that's on this this piece. So the force in the rod, the stress in the rod, is just going to be F over A. Or we could say 70.1 E3, right? This is kilonewtons, divided by my 4.909 E minus 4. And that's going to be equal to, what do we got? 142.8 megapascals. And, oh, and by the way, that's going to be in tension, right? Because I'm in mistake. It's dropping in temperature, so it's contracting. So that's why it's going to end up being in tension. Yes. The shear of the bolt, right? No, so this is actually direct shear. So I might have said in a previous class that we wouldn't be doing any direct shear. But next semester in ME370, we do a lot more of this right here. If you were to take a look at a free body diagram of the bolt, like right here, you'll see that it has these two interfaces right there. So if we just cut the bolt off right here and right there, we would see that, well, on one thing we're actually, here's this part acting onto it, and then here's the other part acting onto here. And so these are actually, this is where the tau is acting across that face right there and across that face. So it's happening in two spots, tau times the shear area of the bolt. And here is that force that's being on there. So you can make the case that the bolt has two shear areas that you need to pay attention to. So the area of the bolt, and we're going to pretend like the stress is across the entire face of the thing, is going to be 2 times pi over 4, 0.016 squared. So we end up getting 4.021 e minus 4 meters squared. And then, so the shear stress that the bolt feels is this V over A. I decided to call it V right in there. And this is not transverse shear. This is direct shear. So we just assume that it's distributed evenly across that face. And so we get the 70,100, right, divided by our 4.021 E minus 4. And we end up with 174.3 megapascals, right? So this is really just walking through things that we know, right? Trying to take little pieces of information and combine them together. I'm not sure I should have brought this up because it just adds too much stuff. I'm not even sure actually everything in this video is maybe not too much for inclusion in class 5. We already did a lot of, I think the pressure, doing more and more complicated pressure vessel problems are probably the real core of what I wanted to accomplish. But I did want to stick this somewhere into the course and wasn't quite sure where it quite fit. It didn't take a long amount of time, and we're not going to dwell on it. But it's something to keep in mind. And maybe I'll try to bring up this topic again some other time in ME370. So something to put underneath your nose, get a little bit of acquainted with, similar to what I have to do later in the semester with buckling. We don't do quite as much work on buckling as I would like. So that's the end of class 5, and let's see how long this video went. I don't know if anyone will watch it. 19 minutes, kind of long. Well, maybe, hopefully it's useful.